Hello, I'm Robert Miller, and what I want to discuss with you in this presentation is the idea of multicollinearity. And you may have been doing some reading in your books. I certainly hope you are doing reading in your books. And if you have, you've certainly, well, if you haven't yet, you will soon, I would imagine. Read about the concept of multicollinearity and how it is a problem in your multiple regression analysis that you need to assess for. And basically, what multicollinearity is about, it's about shared variance among your predictor variables. And you'll note I said among your predictor variables, so your outcome variable, your dependent variable, is not involved in the issue of multicollinearity. This is an issue among your predictor variables. So your independent variables are your predictor variables in your model. And so when we're talking about multicollinearity, let's say we're looking at three predictor variables. And so here we have predictor variable A, and by the way, in the example I'm going to give you now, this would not be an example of multicollinearity. This would be fine if you had this situation. And then here we have predictor variable B, and here we have predictor variable C. And when you look at these three predictor variables, you can see there's some overlap in their variance. So they do share some variance among these three predictor variables, but that's okay. You know, that would not be a problem for your multiple regression analysis. You see, the one thing that multiple regression analyses like live and die for, so like of a multiple regression analysis where a person, it would like wake up in the morning and it would like just go zippity doo-dah, you know, just like jump right out of bed. It would be so happy because it would know that it has another day of estimating regression coefficients. That is what multiple regression analysis and SPSS or any other statistical package that you have loves to do. It loves to estimate regression coefficients for the predictor variables in your model. It just can't get enough of it, and it loves to do it. And it will always do it, no matter what. It is driven to do it, it is obsessed to do it, and is going to do it. The issue for you when it comes to multicollinearity is the conditions under which the multiple regression analysis is going to be estimating those regression coefficients. And are those conditions favorable to estimating regression coefficients in ways that will give you a stable model that can be replicated over time across different samples? Or is the environment for estimating those regression coefficients for the predictor variables in your model such that it's very, adverse for estimating those regression coefficients? Because the multiple regression analysis will always estimate regression coefficients. There's no issue there. But if it really can't do it well, then that means that you'll have a model that is unstable or does not replicate well over repeated samples. Okay, so when you have a situation like this, where you don't have multicollinearity, meaning you have separation among your predictor variables, that if you're looking at this, you can tell predictor variable A from predictor variable B from predictor variable C. Well, just like you can tell those different predictor variables apart, so can your multiple regression analysis. Well, that's a good environment for estimating regression coefficients because your multiple regression analysis can look at these three predictor variables and go, I can tell A from B from C. I can evaluate each of their relationships with the outcome variable, and I can assign a regression coefficient straightforwardly and easily and without bias for predictor variable A and for predictor variable B and for predictor variable C. Nice. We like it when the multiple regression analysis can estimate regression coefficients for the predictor variables like that. Under those kinds of conditions where the predictive variables are well enough separated that the multiple regression analysis can tell them apart from one another and can straightforwardly estimate a regression coefficient for each one of them. So that's a situation where you don't have multicollinearity. But now let's start to shiver now, because we really don't like this. Let's look at a situation where you do have multicollinearity. And this might be a bit of an extreme example, but I hope it makes the point. So here we have one of our predictive variables. And then here we have another of our predictive variables. And then here we have our third predictive variable. So let's see, where's A? Well, I guess A is like right here, I guess. And maybe here's B. Maybe here's C. But man, there's a lot of overlap here. They're sharing a lot of variance with each other. And I don't know about you, but when I look at those three predictive variables, it's tough for me to tell them apart. And just like it's tough for me to tell them apart, it's also tough for your multiple regression analysis to tell them apart. And so if the multiple regression analysis is having difficulty telling one predictive variable apart from the other one, so there's not good separation between them, then the multiple regression analysis will always estimate a regression coefficient for each of those predictive variables, but now it's just doing it just to do it, because it knows it's just driven to do it and it's got to do it, but it doesn't have any confidence in its doing it. And so now we get some regression coefficient that is spit out by your multiple regression analysis for predictive variable A, and another regression coefficient that is spit out for predictive variable B, and another regression coefficient that is spit out for predictive variable C. But those aren't estimates that your multiple regression analysis has any confidence in. It has to estimate regression coefficients for each of your predictive variables, so it does, but not with any confidence, because you can hardly tell the predictive variables apart from one another. They share so much variance with each other. And really, as far as your multiple regression analysis is concerned, they might as well all just be one predictive variable, because it really can't tell them apart. But you will nonetheless get a regression coefficient estimated for each one of them, but not a regression coefficient that you can have confidence in for each of your predictive variables of these three that I've illustrated, which means that you don't have a stable model, or at least for those three predictive variables, they're certainly contributing toward a model that would not be stable and that would not be replicated from sample to sample. So this is an example of where you have multicollinearity among your predictive variables. These are among three predictive variables in your model. And if you see that you do have multicollinearity, and your text will describe different ways that you can assess for multicollinearity, you really have to take steps to resolve that problem so you can get separation among your predictive variables again, so that your multiple regression analysis can provide estimates of regression coefficients for your predictive variables that you can have confidence in. So there you go. That is multicollinearity. Shiver, shiver time. You don't want that.